This set of videos starts our look at higher order differential equations. We have here an nth order differential equation. For the first term, the coefficient function is a sub n of x, and the derivative is dny dxn, the nth derivative of y. Reading this would be a bit tedious, but I'll say we have a sub n of x times the nth derivative of y, and so on until we have a sub 0 of x times y is equal to 0. That's one form of equation that we're going to be looking at in this portion of the course. And another form is, it looks the same on the left, where we have coefficient functions of x. But on the right-hand side, we have a function g of x. And an important distinguishing factor in this chapter is whether the right-hand side is equal to 0 or equal to something that's not 0. In the case that the right-hand side is 0, we would say that the equation is homogeneous. And if g of x is some function other than 0, it could be 2, it could be e to the x, it could be a sine or a tangent. As long as it's not always 0, then we'd say that that equation is non-homogeneous. Another thing to point out is that since these coefficient functions a sub n of x and so on are functions of x, we could see up to the variable x in the coefficient functions, but we won't see the variable y. If we did, these equations would be nonlinear. And all of the equations we're going to look at in this chapter, and for pretty much the rest of the course, are going to be linear equations. As before, we have the concept of initial conditions. In this case, a set of initial conditions would look like y of x naught equals y naught, y prime of x naught equals y1, the n minus first derivative of y at x naught is equal to y sub n minus 1. An initial value problem is one of these types of equations together with a set of these initial conditions. The thing that makes them initial conditions is that the input value x naught is the same for all of these pieces of information. In the event that we have information such as y of a is equal to y naught, y of b is equal to y1, where the input values don't match, then what we have are called boundary conditions, and the resulting problem is called a boundary value problem. And for a boundary value problem, we could have information that says like y of a is equal to y naught, y prime of b is equal to y1. It's not the case that it's a boundary value problem because y is not a derivative. It's the case that the input values don't match. And that's really just the distinction between boundary value problems and initial value problems. For an initial value problem, if all the coefficient functions and the function on the right-hand side, in the case of a non-homogeneous equation, if all those functions are continuous on an interval, and the coefficient function on the highest order derivative is not 0 for that interval, then if the input for the initial value or the initial conditions is in that interval, then the initial value problem has a solution and it's unique. Let me try that again. A differential equation, homogeneous or non-homogeneous, where all the coefficient functions are continuous, in an interval where the first coefficient function is non-zero. An initial value problem with the input on the interval where everything was defined guarantees us that we have a solution and that the solution is unique. All right, I'm not going to say that again. There were two criteria in this statement that we just have been looking at here. It is that the coefficient functions and the function on the right-hand side are continuous, and that the coefficient function on the highest order derivative is non-zero for every x in the interval. These criteria are important, and these two criteria are just going to be assumed moving forward in the statement of theorems about linear equations, meaning from now on we're just going to be assuming that these criteria are true. Now, an initial value problem has a solution that is unique. However, a boundary value problem can have 0, 1, or infinitely many solutions. We're going to look at that now. We're given a differential equation, x squared y double prime minus 5xy prime plus 8y equals 24, and a solution y equals c1x squared plus c2x to the fourth plus 3. It's a 2-parameter family of solutions because we have a c1 and c2. And by the way, later in the chapter, starting with an equation like this, we're going to find a solution that looks like this. For now, our focus is a little different. Given boundary conditions y of -1 equals 0 and y of 1 equals 4, can we find a member of the family of solutions that satisfy those conditions? So let's look at part A here. If y of -1 is equal to 0, then that means when we substitute -1 in place of x, we should get 0. So we would get c1 plus c2 plus 3 is equal to 0. Using the other boundary condition, y of 1 is equal to 4, gives us that c1 plus c2 plus 3 is equal to 4. We can't have c1 plus c2 plus 3 be two different numbers for a fixed set c1 and c2. Therefore, there is no solution that satisfies these boundary conditions. Let's check out part D for contrast here. Our boundary conditions are y of 1 is equal to 3 and y of 2 is equal to 15. That would give us that c1 plus c2 plus 3 is equal to 3, and 4c1 plus 16c2 plus 3 is equal to 15. Some basic algebra will tell us that c1 is equal to -1 and c2 is equal to 1, and so the answer is yes, there is a solution. Or rather, there is a member of the family that satisfies the boundary conditions. Part C offers us an interesting case. The boundary conditions are y of 0 is equal to 3 and y of 1 is equal to 0. Y of 0 equals 3 is going to revert to 3 equals 3. Y of 1 equals 0 gives us c1 plus c2 plus 3 is equal to 0. That means the only restrictions on c1 and c2 is that if you add c1, c2, and 3, you get 0. So we could say here maybe that like c2 is equal to -3 minus c1. Then a solution actually ends up looking like y equals c1x squared plus -3 minus c1x to the fourth plus 3. So we actually have an infinite number of solutions. The question though was, can a member of the family be found? The answer is yes.